With this video, we're getting into the physiology of the heart. I recommend that you review the stimulation of skeletal muscle and the action potential before tackling this topic. We will do a brief review, but can't really reteach the subject. This diagram shows, briefly, the process of skeletal muscle stimulation. First, you have an action potential racing down the axon of a motor neuron. This triggers the release of acetylcholine from the axon terminal, and that acetylcholine triggers an action potential in the skeletal muscle fiber. The action potential travels along the T-tubules and triggers opening of calcium channels in the sarcoplasmic reticulum. When these channels open, you get calcium flooding the cytoplasm, binding to troponin, and opening up the thin filaments so that contraction can happen. Review this if this isn't ringing any bells. This end part is pretty similar in cardiac muscle and in skeletal muscle. You need intracellular calcium. Calcium frees up thin filaments so that myosin can bind, and then myosin walks along the thin filaments, contracting the muscle fiber. However, there are differences in how you get to that flood of intracellular calcium. Probably the most significant difference is that cardiac muscle does not need neuronal stimulation. A few cardiac myocytes trigger their own action potential. These are called pacemaker cells. Yes, pacemaker. Like the artificial pacemakers you can get surgically implanted if your natural pacemaker cells aren't doing their job. When the pacemaker cells fire, calcium comes from extracellular fluid as well as from the sarcoplasmic reticulum. So if calcium levels in your blood are too high or too low, calcium levels in the extracellular fluid will be off and your heartbeat can be thrown off. Third point is that these pacemaker cells are connected directly to other cardiomyocytes via gap junctions. So when the pacemaker cells fire, they trigger the whole heart to contract. Now, this is what the action potential looks like in skeletal muscle and in neurons. You have a stable resting membrane potential. When the cell is stimulated, it depolarizes. It's this increase in membrane potential. Depolarization is followed by a rapid repolarization and a return to that stable resting potential. The cardiac action potential looks pretty different, and there are actually two to talk about. First, you have the action potential in the pacemaker cells, also called the autorhythmic cell, auto self-rhythm, pacemaker self-rhythm cells. The second cardiac action potential is found in the contractile cells, the other 99% of the cardiac myocytes. Here we're looking at the pacemaker cells, the autorhythmic cells. In these cells, the resting potential is unstable. There's a steady rise in voltage. It doesn't stay down at that -70, it kind of leaks upward over time. This is what's called the pacemaker potential. This pacemaker potential happens because the pacemaker cells are leaky to sodium. Remember your concentration gradients? If you're looking, there's outside the cell, there's inside the cell. There's more sodium outside the cell than there is inside the cell. So if the plasma membrane is more leaky to sodium, you'll get sodium ions moving in, making the inside of the cell more positive. This pacemaker potential continues until the cell reaches threshold. Then you get voltage-gated cation channels opening. Cations are just positively charged ions. It's a general term for ions with a positive charge. In these cells, it's calcium ions specifically. So voltage-gated calcium channels open. Calcium flows into the cell and you get that spike in membrane potential. Then the voltage-gated calcium channels inactivate and potassium channels open. Potassium diffuses out of the cell, bringing the membrane potential back down. But it doesn't stay there for long, because you still have that influx of sodium, and the pacemaker potential will eventually bring it back up to threshold, and the cell fires again. The key thing going on here is the pacemaker potential. That's what really makes these cells unique. Next, we have the contractile cardiac cells. The contractile cells are stimulated by cations coming in from neighboring cells. That's what I'm showing here with this green arrow. As calcium ions flood into the pacemaker cells, some diffuse through gap junctions into neighboring contractile cells. This brings the contractile cells up to threshold potential, where voltage-gated sodium channels open up. These voltage-gated sodium channels open rapidly, and you get a very sharp, steep depolarization. Calcium channels open up in these cells as well, but the calcium channels are slow to open and, most importantly, slow to close. They stay open even after the sodium channels close. So the sodium channels close about here, but the calcium channels stay open, so the contractile cell doesn't repolarize right away. Instead, you have this plateau phase where the contractile cells stay depolarized. This plateau phase is the most unique thing about the contractile cell action potential, and it's very important. Look at this refractory period indicator. Remember, the absolute refractory period is the time in which this muscle fiber cannot be re-stimulated to contract. Since the cardiac action potential cannot be re-triggered in this relatively lengthy time period, the heart cannot go into tetanic contractions. If you remember from the skeletal muscle, a tetanic contraction is where the skeletal muscle is contracting so quickly that it never actually relaxes. The heart does not go into tetanus, it always has a relaxation period. This is absolutely critical because the heart can only fill with blood if it's relaxed. A contracted heart has no room for blood to get in, and if the heart can't fill with blood, there's nothing for it to pump out. So, this plateau phase is pretty important, but of course you don't want to plateau forever. The calcium channels do eventually close and potassium channels open. Potassium then diffuses out of the cell, and the cell repolarizes back to its resting potential. There are some key points I want you to understand from our discussion of the cardiac action potentials. We talked about sodium and potassium a lot when you learned about the action potential in skeletal muscle and neurons. In the heart, calcium ions play a big role in the action potential as well. I also want you to familiarize yourself with the differences between pacemaker and contractile cells, and think about how both of them are different from a neuronal action potential. I also want you to think about what's unique about each type of cardiac myocytes. For pacemaker cells, it's that unstable resting potential, the pacemaker potential. For contractile cells, it's that plateau phase that extends the absolute refractory period. Also make sure you understand the significance of these unique characteristics. Lastly, the relationship between pacemaker and contractile cells. Pacemaker cells actually trigger the action potential in contractile cells because cations from the pacemaker cells pass through gap junctions, depolarizing the contractile cells. After studying this video and thinking through those key points, you should be able to address these questions. Compare and contrast the action potentials in neurons, cardiac contractile cells, and cardiac pacemaker cells. Explain the importance of the plateau phase. Describe the phases of the action potential in pacemaker and contractile cells. Discuss how plasma membrane permeability to ions, particularly to sodium, is unique in the pacemaker cells. And think about the significance of gap junctions in stimulating the contractile cells.